If you have been watching my previous lectures on applying conjugate beam method to simply supported beams, you must have realized this, that the end conditions do not change when you convert or when you make a transition from a real simply supported beam to a conjugate simply supported beam. However, when you deal with cantilevers, here the end conditions change, as in the fixed part of a real beam, this is the fixed part, gets converted into a free part or a free end in a conjugate beam, and the free end in a real beam gets converted into a fixed end into a conjugate beam. This is the only rule which you need to follow to solve problems on cantilevers using the conjugate beam method. I expect all of you to remember this. However, we wish to dig deeper, and I'll give you a reason as to why this is followed, why we go from fixed to free and vice versa. There is a specific reason for it. There is a justification. Take a look. If in step number 1, whenever you are applying the conjugate beam method, you make the moment diagram or bending moment diagram, and then you divide it by EI, and then you put it on top of this beam itself. However, we know that we have to change the end condition, fixed to free, free to fixed. However, if you don't change the end conditions, those results could be very, very deceptive. Let me tell you. Let's say if we are going to put this over here, something of this sort, we don't change the end conditions. We make sure that A stays fixed in the conjugate beam also, and B stays the free end in the conjugate beam. By the way, what is this? This over here is a conjugate beam without changing end conditions, without changing end conditions. After you apply method of section, you realize that there is some value of shear force you get, that is some shear force value at A, and there is some value of bending moment that you get again at A. And you know very well for a fact that shear force and bending moment, shear force will give you the value of slope at A in the real beam, whereas bending moment in the conjugate beam gives you the value of deflection at A in the real beam. Taking a look at the real beam, take a look at the real beam over here. You can clearly see if you make a tangent at this very point, that is at A, that tangent has a slope equal to 0. And what do you have here? There is this slope that you've got is not equal to 0. So there is a problem. Okay, that is not feasible. Secondly, this is the fixed portion. Is there any deflection over here? No, sir, there is no deflection. But here, if you don't change the end condition, the final result is that there is some deflection. That means it is not equal to 0. So these two results which we have got when we do not change the end conditions will lead us to wrong results, and that is the only reason why we go from a fixed end to a free end in a conjugate beam, and from a free end to a fixed end in a conjugate beam. So please remember these results. Okay, so far so good. Now we can straight away start solving problems based on this. Example number 5, as per our series, cantilever beam. Here we go. First example, a very, very basic case. What you need to determine is the slope and deflection at this free end. Can be done very easily. I expect all of you to know what method of section is and how shear forces and bending moments can be calculated. This is at least expected from all of you. However, if you don't, you can take a section from this right hand side portion. This is what the sign convention is: shear force upwards, bending moment clockwise. Take a look at this portion of this chunk of the beam. We need to make the moment diagram only. Okay, so let's go for clockwise moment. Minus mx, w into x, again a moment that will, this w multiplied by x will have a clockwise impact at this very point, at this section x. So here it is, mx is equal to wx. Now let's say you want the slope at B, put x is equal to 0. When you put x is equal to 0, the bending moment at B will be 0. And when you put x is equal to L, this value will be minus WL. That is over here. This is how bending moment diagram can be made. And when you divide this bending moment by EI, and when you place this load over here, This becomes your conjugate beam plus, but please note, then you have to convert this fixed part into a free part, and then you have to convert this free part into a fixed part. I hope I have made myself absolutely clear. Okay, now the things are going to be very, very simple. You know that you have to calculate the slope at the free end. One sec. Free end. What is the free end, sir? Free end is B. Right? So if you calculate the shear force, if you calculate the shear force at B for the conjugate beam, you are indirectly calculating the slope at B for the real beam. In the same fashion, if you calculate the bending moment at B for the conjugate beam, this is the conjugate beam, by the way, you are indirectly calculating the deflection at B for the real beam. And by the way, the loads, since the bending moment values are negative, the loads will be pointing in the downward direction. What is this? This is a triangularly varying load. Okay, if I were to convert this triangularly varying load into a point load, how equivalent point load? You just need to take the area, half of base. The base is L and the height is WL over EI. This is the equivalent point load. Where is this going to act? At L by 3 from right angle. Please note this, from right angle. That means from this very point. So the equivalent point load, by the way, is acting here. Okay, and this is that equivalent point load, and that's the magnitude. Let me write the magnitude. This is going to be WL square upon 2EI, right? And this distance is L by 3, and this distance is 2L by 3. This is the basic that we have learned in the previous lectures, right? Okay. Let's start with the shear force calculation. We want the shear force at this very point. So we have to consider this left portion of the beam. When you consider the left side portion of the beam, upward is positive and downward is negative. Okay. Right? So shear force at B, VB is equal to, there is only this triangularly varying load that we have to deal with. So it is going to be equal to half of base is going to be this L. You are going to in fact get this same value, WL square upon 2EI. Base is L and this height, it is this over here. Let me highlight this over here. It's nothing but WL over EI. Let me write this. This is what you get. This actually is a shear force for the conjugate beam, which becomes the slope for the real beam. That is the basic, that is the essence of the method itself. Secondly, we also wish to find the deflection at B for the real beam. Again, get the bending moment for the conjugate beam at B. Idea is very simple. So there is, we can replace this triangularly varying load with this red color arrow, point load, WL square upon 2EI. So it's very simple. Bending moment at B is equal to negative. Okay, it's the case of Hawking. WL square upon 2EI. This value is WL square upon 2EI into this distance is 2L over 3. Done, do the math. This is your deflection, by the way. Okay, now let me show you the results. These are the two values which we've got. And by the way, shear force convention, this is something that you should understand. Okay, it is a case of Hawking, therefore a negative sign. And shear force also, since this is pointing in the downward direction, downward is negative. Let me show you the results. Take a look. Elastic curve. Draw a tangent at this point, and the angle it makes with the positive value of x-axis is your slope. This over here, vertical displacement of B, will give rise to deflection. This is one example. In the second example, take a look. The load is slightly eccentric. It is at a distance of A from the fixed end. However, you have been instructed to calculate the slope and deflection at the free end, that is at end B. How shall we approach this? Again, we'll be applying the method of sections. I know for a fact, if I were to make the bending moment diagram for this case, I know for a fact that the bending moment will be maximum at A. This is going to have some value. Okay. To be very precise, this is going to be equal to WA. And as you move, let's say you're walking on the beam, you'll realize And as you move from A to C, the bending moment will keep on gradually decreasing until you reach W. After W, there is no load on the beam. That means at C, it is going to be 0. And you just need to keep moving. You just need to keep moving. There is going to be no bending moment. Let me green this. So it is 0 here, and WA maximum at the fixed end. However, there is a civilized way of reaching this result. Let me take a section between C and B, and then we are going to again take a section between A and C. Very well. Now, what do we need, sir? We need the moment diagram, which we'll be dividing by EI and then putting on top of the real beam. Obviously, changing the end conditions, which will make it into or transform it into a conjugate beam. MX, is there any other load acting or any load acting? In fact, sir, there is no load acting. If there is no load acting on this portion, why would there be any bending moment? It is simply minus mx equal to 0. Mx is equal to 0. Does not matter. If you put the value of x is equal to 0, you are going to get the bending moment at B. If you put the value of x is equal to L minus A, you are going to get the bending moment at C. Just do it. Do it. Nothing will change. There is no variable. So the bending moment remains same. Now, take a look. Here we have to encounter a load, W. So minus mx minus W into this portion is going to be x minus L minus A. Okay, and here it is. I've written it is going to have a clockwise effect at this section, therefore a negative sign. Mx is clockwise. This is the sign convention, by the way. So this is what you've got. And once you plug in the value of x as L minus A, you are going to find the bending moment at C. Let us see how much it is. Okay, it is now confirmed from both of this result. And when you put x is equal to L, this is what you get. Bending moment at A. Right? That is your bending moment diagram. So far, so good. Now we are going to put this bending moment diagram, and we are going to divide it by EI, and we are going to put it on this beam. But this fixed end will be converted into a free end, and the free end will be converted into a fixed one. That is the only thing you have to do. And please remember, here, since the bending moment was of a hogging nature, all the loads will be pointing in the downward direction. Let me do it quickly. All the loads will be pointing in the downward direction. So far, so good. And again, let me switch on the sign convention. What do you want? You want the bending moment at B, which will give you the deflection for the real beam. You want the shear force at B, which will give you the slope for the real beam. Let us start with this. Shear force at B, VB. There is only one force you need to encounter. It is half of base into height, which is WA over EI. Okay, that is it. Why a negative value? The reason is very simple. You know, if this left portion of the beam has been considered, when you do that, upward is positive, downward is negative. And here this force is acting in the downward direction. That's why we took a negative sign. Secondly, if I were to replace this with a point load, its magnitude again will be equal to WA square over 2EI. Right? Now, as far as moment is concerned, you can find the find its value over here. Again, this is going to have a hogging effect at B, so a negative sign. For a moment, you need a force, you need a perpendicular distance. Very well. So we have both of these things. The force is WA square upon 2EI, so put it over here. Secondly, perpendicular distance. This was the force, by the way. Equivalent point load, WA square upon 2EI. This is that perpendicular distance. How can you calculate this? Sir, it's easy. This over here is L minus A, right? So this over here is A over 3, and hence this much portion will be 2A over 3. So L minus A plus 2A over 3. Done. Solve it. This is what you have. Please note the bending moment for the conjugate beam qualifies as the deflection for the real beam. Okay, so 15 minutes are over. The problem is also over. It has been solved. And let me just review the result for you. What do we want? Sir, we want the slope and the deflection at this free end. Here it is. Please note that this portion of the beam will be bending in a sort of curvy fashion, whereas the portion beyond C until you reach B is a linear one. Okay, why? To let me know in the comments. And why is it so that the slope at C is equal to the slope at B? To let me know in the comments. These are the questions that you must answer after watching this video. Secondly, deflection YB can be shown here. Okay, again, question number 3 for all of you. What will happen when A is equal to L? And can you relate this? Can you relate this to our previous example in this video? Do let me know by sending your comments in the comment section. So guys, if you find this content helpful, and if you believe that this content has helped broaden your knowledge based on mechanics of solids, do give this video a like, share it with as many friends as you can, subscribe to the channel. And guys, this is Manas Patnaik signing off. Take care and have a nice day.